Hello, and welcome to Badger Talks Live, which brings exciting happenings, resources, and talent from your UW flagship campus to the people of Wisconsin and beyond. I'm Rachel McClure. I'm originally from near Boulder, Colorado, but I have been in Madison for the last 4 years as a PhD candidate in the astronomy department. I work on galactic dynamics, specifically bar formation, so galactic bars and galaxies like our own Milky Way. But here I am very excited to introduce Jim Lattis, director of UW Space Place. Joined Dr. Lattis in a history of Washburn Observatory with one of the university's most iconic structures. Behind me today is an image of Washburn, which we'll hear more about. Today, we're going to learn about the building's origins, its most notable astronomers, their contributions to the field, and its role on campus. Jim Lattis holds a PhD in the history of science from UW-Madison and is the author of many publications in that field. He helped create UW Space Place, the Outreach and Public Education Center of the UW-Madison Astronomy Department, and has directed it since its founding. He manages historic Washburn Observatory, teaches courses in introductory astronomy, its history, gives frequent public talks, and consults widely for the media, including UW Communications, Wisconsin and National Public Radio, and other national networks and newspapers. He has also led many trips focused on astronomical tourism.
Well, thank you very much, Rachel. I appreciate the introduction. I'd like to start today actually talking about something that didn't happen at Washburn Observatory, which is the Martian canals craze in the late 19th century, which is relevant because of what it symbolizes about the changing of astronomy in those days. In fact, the Washburn Observatory director, George Comstock, gave a talk to the Madison Literary Club about this topic on the subject of life beyond this world, and he reacted to the observations of Mars by astronomers such as Schiaparelli and others who were claiming that they had seen these features called canals on Mars, and Comstock accepted their observations, although he remained doubtful that it actually was a sign of an ancient civilization on the planet. But even as he was accepting those observations, the opinion among astronomers was swinging away from acceptance of these ideas pretty quickly. And really by about 1910, most professional astronomers had dismissed this idea of canals, although it certainly continued to be a defining topic, continued to be an important thing in media and literature well into the 20th century. The reason I bring this up is because the Martian canal craze really illustrates the limits of astronomy in those days. The canals were illusory. They weren't there, but astronomers thought they were seeing them in their telescopes. They were using their telescopes at the limits, really, that the human eye was capable of reaching, at the limits of the detail that the human eye could manage to see. The human eye was becoming obsolete as an astronomical detector, so to speak, and we're going to talk about detectors. So this kind of work, though, had been extremely successful. This kind of work, I mean the eye at the eyepiece of the telescope, the human eye. When measurements were done with great precision, this was often called the astronomy of precision, and it resulted in a lot of very, very important things: celestial navigation, understanding of distances to the stars, understanding of characteristics and dynamics of stars and binary star systems, even discovery of new pieces of our solar system, like the planet Neptune. And Comstock was a master of such work, this work that was reaching its limits. Comstock worked on binary stars and stellar parallax, but this kind of astronomy was labor intensive, long hours at night at the telescope, long hours of calculation, more or less by hand. And the large amounts of data were needed because the noise, the error of such measurements was very large. This type of observatory, the Washburn Observatory, was really built for this astronomy of precision. Here you see an early picture of Washburn Observatory, and its primary features are designed for the astronomy of precision. The classic Berlin-style observatory, the dome in the middle, the classic dome that houses the equatorial refractor, And then in the west wing, a special type of telescope specifically for measuring star positions, in our case called a meridian circle. That was the Washburn meridian circle there. This type of observatory was intended for exactly this kind of work when it was created in the late 1870s. But by the late 19th century, we're beginning to see the development of what today we call astrophysics. And there are a number of characteristics of this. Part of that is that replacing of the human eye by such things as photographic cameras, spectroscopes, photometers, in place of the astronomer's eye at the end of the telescopes. Another characteristic of this is that we see bigger telescopes, much bigger telescopes coming along, big reflecting telescopes that are replacing the long the classic long refractors that you see sometimes in the cartoons poking out of the domes of the telescopes, but also new questions that astronomers were asking, which are questions about physics of temperatures and compositions and physical processes, magnetic fields, and so on. This transition into astrophysics doomed many 19th century observatories, peers of Washburn Observatory, to obsolescence, but this did not happen at the Washburn Observatory. And so the question we want to answer is, how did Wisconsin astronomy, which started at Washburn Observatory, make the leap from the astronomy of precision to astrophysics? Well, part of it is structural, in that from the very beginning, Cadwallader Washburn, the ex-governor who built the observatory for the university, structured it deliberately from the beginning so that it would be a combination of his private funding coordinated with a partnership with the university in terms of management and the state in terms of funding. And also throughout its history, Washburn Observatory had good institutional support, including state funding, including a campus that was committed to research. And indeed, Washburn Observatory was created as the first research institution on campus. Later support from the Wisconsin Alumni Research Foundation. So structural factors are important, but finally, and the key factor is the push to new technological frontiers by the astronomer Joel Stebbins. Joel Stebbins had come to Washburn Observatory as a student in 1900, as a graduate student, I should say, and studied with Comstock for a year before Comstock, recognizing his talent, sent him off to Lick Observatory, where he got a Ph.D. in astronomy, and then promptly got a job as the director of the little observatory at the University of Illinois. It was at Illinois that Stebbins started collaborating with physicists, which would then be a continuous strategy of his throughout his astronomical career. He developed their photoelectric photometry, which I'm going to talk about a little bit more. And this was successful enough that science done with that technology got him elected to the National Academy of Sciences. By 1921, his old teacher Comstock had recommended him as his successor when Comstock was ready to retire from astronomy. This photoelectric photometry that I mentioned was developed by Stebbins and a physicist named Jakob Kunz at the University of Illinois. They developed detector tubes, which are called Kunz tubes. Kunz made them in his laboratory. You see a picture there in the upper right of a Kunz tube. They started collaborating in about 1913 and were able to develop instruments that could measure that could make quantitative measurements of the intensity of light, and specifically of stars, because star light is very faint and you need very sensitive detectors. This was the challenge all the way along. They did things like measure the varying light of stars that vary in their brightness. You see a brightness curve there on the right, or light measuring the differing amounts of light in different parts of the spectrum. And it's here that history bends for Washburn Observatory. Stebbins came to Madison, handpicked by Comstock, and Stebbins, during the year 1921-22, brought the astronomy of precision to a halt at Washburn Observatory. The meridian circle that I showed you earlier came to was retired along with its principal astronomer, a guy named Albert Flint. And Comstock's micrometer, which he used for double star work, was also retired. The whole orientation of the observatory and the instruments changed beginning in this year, 1921-22. Stebbins completely changed the way that the old refractor was used. Instead of looking through the eyepiece, the refractor became what modern astronomers will sometimes call a light bucket, which just collects and channels light into a photometer. But the methods of photometry, the thing that the Washburn astronomers were doing, required remounting of the telescopes. It also meant that the meridian circle was now just wasting space in the west wing, and they crated it up and stored it away. They began new research projects, entirely new research projects, not continuing at all in the sorts of things that Comstock has done, to explore the interstellar medium, for example, and continuing work on eclipsing variable stars. They also formed partnerships with larger observatories where bigger telescopes were available. And Stebbins actually was a regular user of the largest telescope in the world, the 100-inch out at Mount Wilson. Pushing this technological edge continued with a student that Stebbins hired in about 1931. This student was actually finishing his Ph.D., Albert Whitford, in physics on the Madison campus. So again, collaboration with the physicists. Stebbins gave Whitford the job of trying to build an amplifier that could boost the signal from the weak signal of starlight from these photometers. And Whitford succeeded in that in about early 1932 in creating an amplifier that could take these weak signals and made it possible to detect stars that were about 10 times dimmer than they could with Stebbins's own photometers. This was the equivalent of making the telescope much larger, but it was also, as Stebbins liked to point out, much, much cheaper than getting a bigger telescope. It too changed the way astronomers could work because they no longer had to be near the photometer. They could now be at an operating position. Here you see in the upper right corner there, Albert Whitford at the 100-inch telescope, sitting there at his control station. He's not up hanging on the telescope at all, as the photographers were still doing. Whitford's photometers remained the most sensitive photometers available until after World War II. So they dominated this field of research for quite a while. The amplified photoelectric photometers were used then for a number of scientific purposes, including the eclipsing variable stars, which are a constant along there, but also, and most importantly, for the mapping of interstellar matter by measuring the reddening, which could be done with these types of photometers, the reddening of blue stars, brilliant type B stars. The reddening revealed the extent and depth of the interstellar medium. And it resulted in the first measurements of the first accurate measurements of the size of the Milky Way galaxy. And it also resulted then in more accurate size estimates of what we now know as external galaxies, such as the Andromeda galaxy. So this was remarkable work done here by this new technology that has carried Washburn Observatory into the age of astrophysics in the 1940s and 50s. At which time we get another transition, which really began under Whitford, who succeeded Stebbins. The big part of that being a new observatory out in the west of Madison. So replacing Washburn Observatory for research. And there was reorganization in the astronomy department itself, moving to a new building and expansion of faculty. But then the really earth-shaking thing that happened in October 1957 was the launch of Sputnik, the science of putting the ability to launch objects into Earth orbit, which means platforms for doing science in Earth orbit. And the person who would exploit this most was Albert Whitford's successor, Arthur Code, who became director of Washburn Observatory in 1958. And Code came to Wisconsin with the idea of adapting Wisconsin photometry to space instrumentation, which people had been thinking about for a while before Sputnik actually galvanized the nation to action. In 1958, the U.S. formed NASA, and NASA started creating programs and funding programs A lot of that funding came here to the University of Wisconsin to the Space Astronomy Laboratory that Art Code then created to make projects here to adapt that technology, which in essence goes back to Stebbins' work, but adapt it to space to do, among other things, ultraviolet astronomy in space, because you can't do that from the Earth's surface. This led to a succession of very successful instruments on a variety of platforms, from the early days flying on X-15 and then suborbital rockets, to highly successful satellite instruments such as the orbiting astronomical observatory, instruments for the Hubble Space Shuttle, astronomical instruments to fly, on the Hubble Space Telescope, and instruments to fly also on the Space Shuttle. So this is sketching really quickly the arc of Wisconsin astronomy from the 1920s to the 1950s. They took us from the astronomy of precision right into the exploration of space and the exploitation of space for scientific use, for astronomical use. And again, there are structural things in there that Washburn and the university foresaw how to build a stable research institution. But there's also then the people, the Stebbins and Whitford and Code, who were working at the technological edge for these detectors, trying to always improve these things, looking for new applications, and also accepting the risks and errors that come along with those sorts of things, especially with the space technology, since you can lose your instrument in a moment at launch if things don't go right, as they sometimes didn't in the early days. An important element here also is the succession. These astronomers all knew each other and learned from each other. There's a continuous tradition there. Here's this nice picture from the steps of Washburn Observatory. That's Art Code on the left, Albert Whitford on the right, and first in from the right is Joel Stebbins, and one of Stebbins' students, Gerald Crone, who by then was doing photometry at Lick Observatory, is right there in the blue shirt. So this sort of thing, this continuity of purpose and practice, was another essential element, a very human element of the astronomy that was happening at Washburn Observatory, and that allowed this successful transition from what could have been a dead end in the astronomy of precision into the flourishing astronomy today, both space-based and ground-based astronomy that we have here at Wisconsin. So that's a quick tour. Thank you very much for joining us today. There's much more to go into under other circumstances, but not today. I'll be happy to be taking questions, though, which you can post in the chat. So thanks again.
Thank you for watching this Badger Talks live event produced by the University of Wisconsin-Madison through UW Connect's outreach and the Office of State Relations. Follow us on Facebook and YouTube to see the library of past recorded talks. Please visit badgertalks.wisc.edu to see the schedule of upcoming talks, sign up for the Badger Talks email list, and search the roster of over 400 UW experts who are available to give talks on important issues in your Wisconsin community.